Spider-Derivative Man, back talking to you about rates of change. Another quick question. Why did Bruce Wayne's dentist give him mouthwash? Because he had bat breath.
First thing we're talking about is a rate of change. That's a ratio between a change in one variable relative to a corresponding change in another variable. Graphically, the rate of change is represented by the slope of a line. So here you could see this blue line right here. If we were to take the slope of that, it would give us the rate of change, or the change in the y over the change in the x, or the change in the distance over the change in the time. So if we were to pick out 2 points on the graph, we could figure out the rate of change of our particular function here, the change in the distance over the change in time. So when we travel 80 miles, it takes 2 hours. You could also look at when we travel 240 miles, it takes 6 hours. So if you were to simplify that, you would end up getting a change of 40 miles over 1 hour. For every 40 miles you travel, it takes 1 hour, 40 miles per hour. That's where the rate of change comes from. Now, the instantaneous rate of change, that would be the rate of change at a particular moment. This is going to be the same as the value of the derivative at a particular point. For a function, the instantaneous rate of change at a point is the same as the slope of the tangent line to the graph at that point. A couple things in here. First, the rate of change at a particular moment is the instantaneous rate of change. Now, the instantaneous rate of change is just going to be the slope of your function at a particular point. Now, sometimes you have a curved function, which is why this is good to know. The derivative of a function at a particular point is going to give you the instantaneous rate of change, or the slope at that particular point. So you can see here, the instantaneous rate of change at 1, 1 is going to be equal to the slope of this red curve at 1, 1, which is equal to the slope of this blue tangent line. All of those three things are going to be equal to one another. They all mean the same thing. Now, the position function is the function s of t that gives the position relative to the origin of an object as a function of time. So the position function, if you plug in a specific x value or t value, it will give you the position of an object at that particular moment in time. It'll tell you how far left or how far right or how far up or how far down a particular object is. The displacement is going to be the change in position s of an object from time A to time B. So for example, down here, given a position of an object, s of t, right, that's your position function, the displacement of that object from time A to time B is the change in position, which is equal to s of b minus s of a. Your y value where it ends minus the y value where it starts. Time A, our object is at this particular position. Then we travel all the way to time B and our object is at this position. Then the displacement is going to be s of b minus s of a. That's going to be how far the object moved, up or down, left or right, whatever we're measuring in terms of position.
Now, higher order derivatives. It says if f of x is a differentiable function, then its derivative f prime of x is also a function and may have a derivative, finite or not. This function is called the second derivative of f of x and is denoted f double prime of x. So all this is talking about is when you take the derivative of a function, f, you get f prime of x. And more often than not, you can take the derivative of your derivative. And if you take the derivative of your first derivative, you get something called your second derivative, which is f double prime of x. And if you take the derivative of your second derivative, you get your third derivative, which is f triple prime of x. And then you can take the derivative of that. And notice that the fourth derivative, the primes go away, and you just write a number up here for what derivative you're taking.
Now, the average velocity or slope of a secant line is the change in position over change in time, or delta s over delta t, over that period of time. What this means is that given a position of an object, s of t, that is your position function, the average velocity of the object from time A to time B is going to be equal to the slope of your secant line going through those 2 points. So if you have A comma S of A and B comma S of B, remember A and B represent your time, and S of A represents where the object is at time A, and S of B represents where the object is at time B. If you take those 2 points, calculate the slope between those 2 points, you get your average velocity over that period of time, or the slope of your secant line Q. All of those three things mean the same thing. Please note that this can be used to approximate your instantaneous velocity of a function using values of a and b that are close together. So if you're given a table of values, and let's say you have time 2 and time 4, and then you have positions at time 2 and a position at time 4, and it says approximate the velocity at time 3. Then you would just calculate the slope between the 2 points at time 2 and time 4, and you would get an approximate instantaneous velocity for time 3.
Now, the velocity of an object, all this is saying is that your velocity function is equal to the derivative of your position function. So v of t, your velocity function, is equal to s prime of t. So if you take the derivative of your position function, you get the velocity function. That's what this is saying. Speed is just the absolute value of velocity. So if you get the velocity of an object, but it wants the speed, just make sure it's the positive version of whatever that velocity is. So your velocity can be positive or negative because that's telling you what direction it's going. Speed, we don't care about direction. We just care about the magnitude. How fast is it going? Now, acceleration of an object is just the derivative of your velocity. So the acceleration function, a of t, is equal to the derivative of your velocity function. It's also equal to the second derivative of your position function. So if you have your position function and you take the derivative of that, you get your velocity function. If you have your velocity function, you take the derivative of that, you get your acceleration function. So again, acceleration is the derivative of velocity, and the units for velocity are distance over time. Because of that, when we take the derivative here, we end up getting acceleration units are distance over time squared. So if your velocity units for whatever you're measuring are meters per second, then your acceleration units will be meters per second squared. Make sure you know that your velocity units are going to be distance over time, and then your acceleration units are always going to be distance over time squared.
Now, the position of a free-falling object, neglecting air resistance under the influence of gravity, can be expressed by the equation s of t, position, is equal to 1/2 gt squared plus v sub 0 times t plus s sub 0, where s of t is the object's position at time t, g is the acceleration due to gravity, v sub 0 is the initial velocity of the object, and s sub 0 is the initial height of the object. And over here, you can see that the acceleration due to gravity is usually going to be negative 32 feet per second squared, or if you're using the metric system, it would be negative 9.9 meters per second squared. That's what you would plug in for G. Here is exactly what you need to know for the AP test. The first is that the velocity function is equal to the derivative of the position function. The second would be that the velocity function, when that's positive, when you have a positive velocity, this implies that the object is either moving right or up. If the velocity is negative, so if your velocity is less than 0, this implies that your object is either moving left or down. It depends on which plane your object is moving. Fourth, the speed is equal to the absolute value of velocity. And we said that's because speed ignores direction. The velocity will tell you the direction based on whether it's positive or negative. So if it's positive, it's going to move right or it's moving up. If it's negative, it's moving left or down. But speed ignores direction. It's just the absolute value of velocity. The velocity function, when that velocity is equal to 0, this implies that the object is either stopped or it's changing direction. It's changing from going left to going right, or it has stopped going up and is now coming down at that particular point. So if the velocity is equal to 0, the object is either stopped or it's changing direction. Part 6, the acceleration is equal to the derivative of the velocity function, which is equal to the second derivative of the position function. So if you start with your position function and take the derivative of that, you get the velocity function. If you take the derivative of that, you end up with the acceleration function. If acceleration and velocity have the same sign, then your object is speeding up. So if acceleration and velocity are both positive or both negative, your object is speeding up. But if your acceleration and your velocity have opposite signs, then your object is going to be slowing down.
Time to beat the Green Goblin. It's example time.
Now, example 1 says find the average rate of change of the function over the given interval. Compare this average rate of change, or average velocity, with the instantaneous rates of change at the endpoints of the interval. So here's our function, and here is our given interval. Now, this is our time, which means we need to get the position of our function at those specific times. So we need to plug in each of these endpoints. So let's plug in 3 first, and we end up getting a position of 2. If we were to plug in 3.1 to our function f, then we end up getting a position of 2.61. Now, in order to find the average rate of change, we're going to take delta f, because that's our function here, over delta t, which is equal to the change in the y's over the change in the x's. So 2.61 minus 2 over 3.1 minus 3, and that ends up getting you 6.1. So that is your average rate of change over this given interval. That is the same as the average velocity over this given interval. Now, the instantaneous rates of change, in order to figure those out, what we would do is we would take the derivative of our position function. So we end up getting f prime of t is equal to 2t plus 0, which is just 2t. Now, if we wanted the instantaneous rate of change at time 3, we would take the derivative of f, which we did, and plug in 3 for t, which we're doing right here, and we end up getting 6. If we were to do it at 3.1, we do the same thing, and we end up getting 6.2. So you can see that your average rate of change is just the average of your instantaneous rates of change at those endpoints. Here, we have our new position function h of x, and we have our interval right here. So the first thing we're going to do is find the average rate of change, but we need to find our y values or position of our graph at these given endpoints. So we're going to plug in 0 for x, and we end up getting 1. If we plug in 1 for x, we end up getting approximately 3.718. If we wanted to figure out our average rate of change, that would just be delta h over delta x this time, because we're not using t anymore, we're just using x. So what we do is we do the change in the y's over the change in the x's, so that would be the change in your h of x over the change in x. So 3.718 minus 1 over 1 minus 0, which comes out to 2.718. That's going to be your average rate of change. Now let's compare that to the instantaneous rates of change at the endpoints. So we take the derivative of our function over here, the derivative of x squared plus e to the x is going to give you 2x plus e to the x. So then you plug in 0 for your first endpoint and you end up getting 1. If you were to plug in 1 for your second endpoint, you end up getting 4.718. So yes, you can see that your average rate of change is the average of those two endpoints.
You try.
First, we have our function right here, and we want to find the y values that go with the endpoints. So here we have 84 feet when t is equal to 1, and then when t is equal to 2, we have 36 feet. Now, to find the average rate of change, that's delta s over delta t, which is the change in your y's over the change in the x's, or change in s over change in t. So you simplify that by subtracting 84 minus 36 over 2 minus 1, and get negative 48 feet per second, which is going to be your average velocity over that given time. Same thing down here, plug in your endpoints, and you end up getting your y values that go with those endpoints, or your position of the object at that particular moment in time. Then what you can do is find the average rate of change by delta s over delta t, and you end up getting negative 40 feet per second. Now, example 2 says a ball is thrown straight down from the top of a 220-foot building with an initial velocity of negative 22 feet per second. What is its velocity after 3 seconds? What is its velocity after falling 108 feet? So first thing you need to do is create your position function. You know your position function is going to be based on this. Now what you got to do is plug in each of your given variables. So you're given your initial height, because it's a 220-foot building and you're at the top. So that's going to be your initial height. Your initial velocity is going to be negative 22 feet per second. And your acceleration due to gravity, since we're using feet per second, is going to be negative 32. So plug in each of those variables and you have your position function. Now it says, what is the velocity after 3 seconds? So what we can do is we can take the derivative of your position function. If we take the derivative of your position function, we end up getting the velocity function, which is negative 32t minus 22, because the derivative of t squared, bring that 2 down, and you end up getting negative 32t. T here, the derivative of t just becomes 1, and you're left with this. So your velocity function is here. Now, your velocity after 3 seconds means you plug in 3 for t, and you end up getting your velocity after 3 seconds, which is negative 118 feet per second. Now that we have that, we can move on to answering the next question, which is, what is the velocity after falling 108 feet? So if you start at a 220-foot tall building and you fall 108 feet, what is the position of the ball? So the ball would then be at a position of 112 feet, because it started at 220, fell 108, is now at 112. So you're going to set your position function equal to 112, and now we can solve for t. So we can figure out that t and then plug it in the velocity function. So let's go ahead and do that. We subtract 112 on both sides, then we can factor out a negative 2 and factor this quadratic trinomial in here, and we end up getting 8t plus 27 times t minus 2, You then set each of these equal to 0, and you end up getting values for your time at 2 and negative 27/8. Now, we're not dealing with negative time. You can't go back in time. We're starting at time 0, where we hold the ball, and then after that, we release the ball. So before that, we're not dealing with that. So there is no negative time here. So our only time left is time 2, and you can figure out the velocity by plugging in that 2 to the velocity function and getting a velocity of negative 86 feet per second. First, we need to write our equation, and we're using this time meters per second. So the acceleration due to gravity is going to be negative 9.8 meters per second squared. We also know that the initial velocity is 100 meters per second, and you're shooting from the surface of the Earth. Therefore, your initial height is 0. Plug those in, you would get your position function. Now it says, what is the velocity after 5 seconds? So the velocity after 5 seconds, we need to take our position function and take the derivative of it. So we use our power rule, bring that 2 down, multiply it to the negative 4.9. You end up getting negative 9.8, and then the t right here just becomes 1. So we have our velocity function. Once we have that, we can just plug in our 5, and we end up getting a velocity after 5 seconds of 51 meters per second. After 10 seconds, we just take that same velocity function, plug in our 10, and we end up getting 2 meters per second. Example 3 says match the following position function graphs with their corresponding velocity function. So this is kind of like what we did in 2.1, except this time it just has your original function as your position function and your derivative function as your velocity function, because velocity is the derivative of the position function. So A is right here, and remember the velocity functions, your y values are going to correspond with the slopes of the tangent line to the graph of your position function. So the slopes here are positive, 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 and then get very positive as time increases. So which y values get more and more positive as time increases? That would be this one right here. Your y values get more and more positive as time increases. So that matches with D. For B, we have the slopes of our tangent line start off very positive and then get more and more and more towards 0 as time increases. So which y value starts off positive and gets more and more and more towards 0? That would have to be C right here. For C up here, the slopes of our tangent line start off positive and then go to 0 around the middle and then go negative after that as time increases. So which y values start off positive and then go to 0 around the middle and then go negative after that as time increases. That would have to be A right there, which means that D is going to have to correspond with B, because you start off with a positive constant slope and then at the middle of your graph it changes to a constant negative slope. So that would have to be this one right here.
You try.
First, if we're looking at A, we're just looking at the slopes of the tangent line to the curve, and those should correspond with the y values of the velocity function. So the slopes of the tangent line to the curve start off positive and then get more and more and more towards 0, but are still positive. So that would have to be positive y values. They get more and more and more towards 0. That would be B right there. For B, we have a constant graph right here. This is a constant function, which means the slope is just 0. So you're looking for a graph that is just of y is equal to 0. That would have to be C right here. For C up here, we have a constant negative slope, and then at x is equal to 5, it changes to a constant positive slope. So the derivative of the graph is going to have y value that is a constant negative number, and then changes to a constant positive number at x is equal to 5. That would be A. And then for D, the slope of your tangent line to the curve would be positive, and then around x is equal to 2, it becomes 0. And then after x is equal to 2, it gets more and more and more negative. So which y values start off positive and then go to 0 around the middle, and then go negative after that as time increases. That would have to be this guy right here. Now example 4 says a particle P is moving on the number line showed below. The coordinate plane over here is going to be the position of P as a function of time. Now it says, when is P moving to the left? When is it moving right? When is it standing still? So this particle is moving left and right on a number line. And this is telling you where the position of the object is over the given time. Now it says, when is P moving left? Remember, when velocity is greater than 0, this implies the object is moving right. When velocity is less than 0, when it's a negative number, this implies the object is moving left. And when velocity is equal to 0, that implies the object is standing still. So if this is the position of the particle, then the velocity is going to be the derivative of the position function, which means it's going to be the slope of the given function at any point on the graph. We want to figure out first, when is it moving right? It's when the velocity or derivative or slope of the tangent line to the graph is going to be positive. So when does this graph have a positive slope? That would be from 0 to 1.5, right? From 0 to 1.5, it has a positive slope. And then from 3 to 4.5, we also again have a positive slope. And that's about it for positive slopes, right? So we can say that the object is moving right when we have a positive velocity, which means that object is moving right on 0 to 1.5 and 3 to 4.5. Object is moving left when we have a negative velocity, or when the slope of our tangent line is negative. That would be from 6 to the end, right? Even though it's a different velocity, they're both still negative, which means it's moving left. V of t is equal to 0 implies that the object is standing still. Now, when is the object standing still? When we have a velocity that's equal to 0, which means the slope of our tangent line is a horizontal line. So that would be from 1.5 to 3, and then from 4.5 to 6. Both of those intervals give us a 0 slope of our tangent line. Now, let's graph the particle's velocity and speed where defined. So we're first going to graph the velocity. So the velocity from time 0 to time 1.5 is going to be a positive, and it looks like up 2 over 1, so it would be a positive 2. So from 0 to 1.5, we have a slope of 2. That means our velocity is 2 over that time. Then from 1.5 to 3, we have a horizontal slope of our tangent line, which means the velocity is 0. So from 1.5 to 3, we have a 0 velocity. Then from 3 to 4.5, we have a slope of up 2 over 1.5, which is about 1.333. So we'll put that there. That's going to be our velocity over that given interval. And then again, from 4.5 to 6, we have a velocity of 0. Then from 6 to 7, we have a velocity of down 2 over 1, so that would be negative 2. And then from 7 to 9, we have a velocity of down 1.5 over 2. That would be about right here. That's your velocity over that given interval. Now, if we want to do speed, remember speed is just the absolute value of velocity. So if your velocity is positive, then your speed is going to be the exact same thing. If it's 0, it's going to be the same thing. Positive, same thing. That's your speed. 0, same thing. But if your velocity is negative, your speed is going to be the absolute value of that. So instead of being negative 2, it's actually going to be positive 2 from 6 to 7. Instead of being negative 0.8 or something, it's going to be positive 0.8 or something. That's how speed works, okay? Remember, it's the absolute value of velocity.
You try.
Okay, so the figure shown below gives the velocity v equals f of t of the particle moving along the coordinate plane. Now this time it doesn't have the position, it has the velocity as your y-axis. So it says, when does the particle move forward? When does it move backward? Now remember, forward and backward, up and down, left and right, that just is referring to when your velocity is positive or negative. So if your velocity is positive, your object is moving forward. When it's negative, we're saying it's moving backward. So velocity this time is on the y-axis. We're not doing slope this time because the velocity is graphed here. This is the graph of the velocity. So when your velocity is positive, that just means when the y values are positive, your object is moving forward. So when all the y values are positive, that would be from 0 to 30, your object is moving forward. When your velocity is negative, when all the y values are negative, your object is moving backward. So that would be from 30 to 55. Next, it says, when is the particle's acceleration positive, negative, and 0? So remember, acceleration is the derivative of the velocity function. So if I wanted to figure out when acceleration was positive, I would figure out when the slope of the tangent line to the curve, or just when the slope of this linear function is positive. That would be when my acceleration is positive. So acceleration is positive from 0 to 10. It's also positive from 40 to 55, right? We have positive slopes there, positive slope there. Then your acceleration is going to be negative whenever you have a negative slope. So if it's negative from 15 to 40, that would mean that your acceleration is negative over that given time. Then the acceleration is 0 anytime you have a horizontal slope. So that would be from 10 to 15. That would be an acceleration of 0 over that time. Now part C says, when is the particle moving at its greatest speed? Now remember, speed is the absolute value of velocity. So you could pick a positive or a negative velocity, just whichever gives you the greatest absolute value. Here, it's going to be at positive 60. That's going to be the highest speed that it travels, 60 meters per minute. It travels that speed over the given interval, 10 to 15. Then part D says, when is the particle speeding up and slowing down? So if your acceleration and velocity have the same sign, your object is going to be speeding up. So if they're both positive or both negative, then your object is going to be speeding up. It's going to be slowing down if your acceleration and velocity have opposite signs. So if one is positive and one is negative, or vice versa. So where do we have an acceleration and velocity that is both both positive. Here, you can see from 0 to 10, we have a positive velocity. Your y values are positive. And the slope of your tangent line to the curve is also positive, right? You have a positive slope here. Therefore, the object must be speeding up from 0 to 10. Then from 30 to 40, you have a negative velocity, but you also have a negative slope of your tangent line. Therefore, it's speeding up in the opposite direction. So speeding up here, speeding up here. Next, they have opposite signs when you have a negative slope here, but you have positive y values. Therefore, it's slowing down from 15 to 30, and then again, it's slowing down from 40 to 55 because you have a positive slope, but you have negative y values.
Now, example 5 says the velocity of an object in meters per second is v of t equals 36 minus t squared, for 0 is less than or equal to t, which is less than or equal to 6. Find the velocity and acceleration of the object when t equals 3. What can be said about the speed of the object when the velocity and acceleration have opposite signs? Okay, so what does this want us to find? It wants us to find the velocity and acceleration of the object when t is equal to 3, so at 3 seconds. So how do we find the velocity at time t equals 3? Well, we take our velocity function, which is 36 minus t squared, and we're going to plug in 3 anywhere you see a t. So if this is our function, we take 3, plug it in here and here. So v of 3, the velocity function at time t equals 3, is equal to 36 minus 3 squared. What's 3 squared? That's 9. What's 36 minus 9? That's 27. Now remember the units we were using? The velocity of an object in meters per second means our velocity should be in meters per second. Now we also want to find the acceleration of the object when t equals 3, but we're only given the velocity function. How do we find the acceleration function? Well, if you recall, acceleration is the derivative of velocity. So if we take our velocity function and find the derivative of that, then we can find the acceleration function. So what is the derivative of 36 minus t squared? Well, we take the derivative of each term separately. Derivative of 36 is just going to be 0. Derivative of t squared is going to be 2t to the first. And 0 minus 2t to the first is just negative 2t. That's our acceleration function. But that's not what it wanted. It wanted the acceleration of the object when t is equal to 3. So how do we find the acceleration at 3 seconds? Well, we take 3 and we plug it in for t in the acceleration function. And what is negative 2 times 3? That's going to be negative 6. Now remember, because our velocity is in meters per second, our acceleration then must be in meters per second squared. Acceleration is distance over time squared. Make sure you put the correct units on velocity and acceleration. Lastly, this says, what can be said about the speed of an object when the velocity and acceleration have opposite signs? So in this case, our object has a positive velocity but a negative acceleration. Positive velocity means your object is going to the right or it's going up. The negative acceleration means that it's slowing down to the right or slowing down on the way up. So when the velocity and acceleration have opposite signs, it means an object is slowing down.
The itsy bitsy spider went up the water. You try!
Okay, this says the velocity of an object starting from rest is v of t is equal to the quantity 100t divided by the quantity 2t plus 15, where v is measured in feet per second. Find the acceleration at 5 seconds, 10 seconds, and 20 seconds. So note, in this question, it just wants us to find the acceleration at specific times, meaning we don't need the velocity function. But why do they give it to us then? Well, in order to figure out the acceleration function, we need to take the velocity function and take the derivative of it. If we know the derivative of the velocity function, we know the acceleration function. So how do we take the derivative of this here? Well, we have variables in the numerator and denominator. We're going to have to use the quotient rule. And the quotient rule says we need to take the derivative of the numerator times denominator minus numerator times derivative of denominator all over denominator squared. So how do we simplify this? Well, derivative of 100t, 100 is just a constant, so we can move that out front. Derivative of t is just 1, so we get 100 times 1. Over here, derivative of 2t plus 15, we got to take the derivative of each term separately. The derivative of 2t is just going to be 2 times 1, and then derivative of 15 is just going to be 0. Now, we can simplify this. 100 times 1 is 100. 2 times 1 plus 0 is just 2. If we multiply that to this negative 100t, we get negative 200t. And if we multiply this 100 to the 2t and to the 15, we've got to distribute it. This is what we get. Now, the 200t and the negative 200t are going to cancel each other out, and we're left with 1500 over 2t plus 15, the quantity being squared. Now, what did we just find? We found the acceleration function. So we can use this acceleration function to now find the acceleration of our object at 5 seconds, 10 seconds, and 20 seconds. So let's first find it at 5 seconds. We take our acceleration function and we're going to plug in 5 for t, because that's going to tell us what the acceleration was at 5 seconds. Now, when we simplify this and write our units, it's going to be 2.4. Now remember, the velocity was in feet per second, so the acceleration then should be in feet per second squared, distance over time squared. That's acceleration. Let's find it at 10 seconds now. At 10 seconds, we're going to plug in 10 for t to our acceleration function. We simplify and we end up getting an acceleration at time t equals 10, or 10 seconds, of 1.2 feet per second squared. Doing the same thing at time t equals 20, or 20 seconds. We plug in 20 for t in our acceleration function. We simplify and we end up getting 0.5 feet per second squared, meaning the acceleration is decreasing as your time increases. Now, example 6 says match the following position function graphs to their corresponding velocity and acceleration functions. So we've done this before, except this time now we have position, velocity, and acceleration. We have all three of these functions. So let's start with our position function. Starting with A, we want to match it with its corresponding velocity function. Now remember, the slopes of the tangent lines to the curve of my position function, my original function, correspond to the y values of the graph of the derivative, or in this case, the graph of velocity. So let's look at graph A. The slopes of the tangent line to the curve are positive, and as time increases, these slopes get more and more and more positive. So we are looking for y values in the graph of our velocity that start off positive and get more and more and more positive. Well, that would have to be D here. We have y values that start off positive and get more and more and more positive as time increases. Now let's figure out which acceleration graph matches with this velocity graph. Again, acceleration is the derivative of velocity. So that means that this graph, if we're looking at the slope of this graph, it's just a constant positive slope. So that would match with a constant positive y value down here in the graph of acceleration. So which of these has a constant positive y value? Well, if this is our t-axis, then this would be a constant positive number. So D would match with B. There we go. We got all three. Now let's go with B. If B is our position function, we are looking for y values down here that match the slopes of the tangent lines to the curve, because velocity is the derivative of position. So the slopes of the tangent lines to this curve start off very positive and then get less and less and less positive as time increases and approach zero. So which y values here start off positive and then approach zero as time increases? That would be this one right here, graph of C. Then we do the same thing. Acceleration is the derivative of velocity. So which of these graphs down here have y values that match the slope of this graph? Well, this is a constant negative slope, so we're looking for a y value that is a constant negative number. So that would be this one, and that would be this one. So let's look up here. This has a constant negative slope, and so does this one. Well, this slope is more negative than this slope. So we know that this must be the more negative y value, which means this graph should match with this one as its derivative. Now let's go to C. C is a graph that starts off with slopes of its tangent lines that are very positive and then get less and less and less positive, and then right around the middle of our t-axis we get a slope of 0, and then these slopes get more and more and more negative as time increases. So we're looking at the velocity function, the derivative of the position function, and we're looking for y values that start off positive and then approach 0 towards the middle and then get more and more and more negative as time increases. So C would have to match with A right here. We again saw that the graph of C right here had a constant negative slope that wasn't as steep as this one, which is why the derivative of this graph would be this one right here. Since this one over here, the y value is less than this one over here, we can see that D would have to match with A right here. Lastly, the graph of D is our position function. It is a constant positive slope followed by a constant negative slope. We got a corner. So in our velocity function, we need a y value that is a constant positive number followed by a y value that is a constant negative number. That's why D matches with B right here. And then the derivative of our velocity function would be our acceleration function. So we're looking for a 0 slope followed by a 0 slope. So 0 slope, 0 slope, that would be C right here. So that's how those work.